To bridge this semantic gap, we need to teach computers to understand data like we do. The solution lies in converting our rich, complex world into a universal language that machines can process, the language of numbers. This is the fundamental concept of a vector. A vector is simply a list of numbers that represents the essence or meaning of a piece of data, whether it's a word, an image, or a sound. So, how is this magical translation from data to a meaningful vector performed? This is the work of highly specialized AI models called embedding models. These models are trained on colossal datasets, allowing them to learn the intricate relationships and contexts between different concepts. The output they produce is a vector, often called an embedding, which is a dense numerical fingerprint of the input data. Now that we have these embeddings, we can plot them as points in a high-dimensional space we call the vector space. While we can't truly visualize hundreds of dimensions, the core principle is beautifully simple. In this space, distance equals meaning. Items with similar meanings, like king and queen, will have vectors that are very close together, while dissimilar items, like king and turtle, will be far apart. To precisely measure the closeness we just saw in the vector space, we use mathematical formulas called distance metrics. The most common for high-dimensional data is cosine similarity, which, instead of measuring straight-line distance, measures the angle between two vectors. A small angle means the vectors point in a similar direction, indicating high conceptual similarity. This is the key to ranking search results by relevance. We now have all the pieces: data converted to vectors, organized in a vector space, and a way to measure similarity. But what happens when you have billions of vectors? The simple approach, a brute force or exact nearest neighbor search, would require comparing your query vector to every single one of those billions. While perfectly accurate, this is computationally explosive and far too slow for any real-time application. This massive scaling challenge is the very reason we need a specialized solution. Having identified the scaling problem, we can now introduce the hero of our story, the vector database. This is not just a place to store vectors, it's a highly specialized system purpose-built for one primary task: performing incredibly fast similarity searches on massive datasets. Its core function is to find the nearest neighbors to a query vector in milliseconds, not hours, by using clever shortcuts instead of brute force. The magic behind a vector database's incredible speed lies in its indexing algorithms. Instead of scanning every vector, the database pre-builds a smart data structure, like a multi-layered graph, that organizes the vectors based on proximity. When a query arrives, this index acts as a super-fast navigation system, guiding the search directly to the most promising neighborhood in the vector space and completely ignoring irrelevant regions. This is the core principle of Approximate Nearest Neighbor, or ANN search. This incredible speed from ANN search comes with a small, intentional trade-off between perfect accuracy and blazing fast performance. Instead of guaranteeing the absolute, mathematically perfect nearest neighbors, ANN algorithms aim to find good enough or almost perfect neighbors. For most applications, the difference is imperceptible to the end user, but the performance gain is monumental, often reducing search times by orders of magnitude. To make this concrete, let's examine a popular and powerful AN algorithm, HNSW, which stands for Hierarchical Navigable Small Worlds. HNSW builds a multi-layered graph structure over the data. The search begins at the top, sparsest layer, with long-range connections, allowing it to quickly zoom in to the right region of the vector space. It then descends through progressively denser layers, refining the search until it finds the nearest neighbors at the bottom layer. A truly powerful vector database, however, doesn't just handle vectors. It also stores associated metadata like product IDs, dates, or user tags alongside each vector. This unlocks filtered search, a hybrid query that combines semantic similarity with precise, structured filtering. For example, you can search for a dress similar in style to this image, but only from results where the metadata shows it's size medium, blue, and in stock. With this full picture of how vector databases work, let's explore their transformative applications. The most direct is semantic search. Unlike keyword search, which would miss an article on economical, speedy automobiles if you searched for fast, cheap cars, semantic search understands your intent. It retrieves results based on their conceptual meaning, providing far more relevant and comprehensive answers. Vector databases also power the recommendation systems that feel like they can read our minds. When you interact with content, like watching a movie or liking a product, the system updates a user profile vector representing your tastes. To find recommendations, it simply searches the vector database for item vectors that are closest to your profile vector. This proximity-based matching is how platforms suggest new content you're highly likely to enjoy. Beyond recommendations, vector databases are exceptionally good at anomaly detection. In a dataset of normal operations, like server logs or financial transactions, the vectors for these events will form a dense cluster in the vector space. An unusual event, such as a cyber attack or a fraudulent transaction, will have a vector that lies far outside this main cluster, making it easy to flag as an outlier. This spatial isolation is a powerful signal for identifying rare and critical events. The power of vectors isn't confined to text. By using different embedding models, we can convert images, audio, and even protein structures into the same shared vector space. This enables multimodal search, where you can use one type of data to search for another. For example, you could upload an image of a jacket to find similar-looking jackets for sale. Or even use a text description like a red leather jacket with silver zippers to find corresponding product images. Perhaps the most revolutionary application today is Retrieval Augmented Generation, or RAG, which supercharges large language models. LLMs have immense general knowledge but lack access to your private, real-time data. RAG solves this. When a user asks a question, the system first queries a vector database to retrieve relevant factual context. This context is then fed to the LLM along with the original prompt, enabling it to generate accurate, context-aware answers grounded in real data. With so many powerful applications, the vector database ecosystem is growing rapidly. You'll encounter options ranging from open-source libraries like Face, which you manage yourself, to dedicated open-source databases like Milvus or Weaviate, and fully managed cloud services like Pinecone. The right choice depends on your project's scale, performance needs, and engineering resources. But the core principles we've discussed today apply to all of them. Let's summarize the incredible advantages vector databases bring to the table. First, they provide true semantic understanding, moving beyond keywords to grasp intent. Second, they offer extreme speed at scale, making searching billions of items possible in milliseconds. Third, they master unstructured data, turning images, audio, and text into searchable assets. Finally, they unlock next-gen AI applications like RAG and real-time recommendations, which were previously impractical. In conclusion, vector databases represent a fundamental paradigm shift in how we interact with information. They are the architectural foundation for a more intuitive, context-aware generation of AI. By providing a semantic brain for applications, they move us from a world of rigid queries to a future of fluid, meaning-driven conversations with our data, unlocking potential we are only just beginning to explore.